course, this is not the term that you will find in text, because this is just a baby case of something bigger that one can prove. But I think for an introduction, this is a good start. So this is what we prove. We've seen that U act on G mod gamma. Maybe I should recall what the letters are, right? But is ergodic. G mod gamma as a probability measure. This we didn't prove yet. I will actually prove. Maybe I'll eventually on it. What are just notation? G is equal to R. Gamma already very defined. U is the unipotent mode. Which is said is isomorphic to the antiprix. And maybe I should recall we had this nice picture of U orbits on the border square. Now, since I understand much better the U action on R2 than the gamma action on R2 somehow on one end, and in a similar way I understand quite well, in a sense, the action of U on G mod gamma, then maybe I will adhere to this duality principle. Somehow, okay. What we have here, oh, maybe I should. I'm having this phi. It goes from R2 to R2, but actually it's G mod U to G mod 1 to R2. Somehow I want to use the fact that this is a G coset space. This is some G space. This is a gamma, right? This is some G space. This is a space which is G homogeneous variety. Both are algebraic varieties. I'm not using this in a formal way. I'm using this, our explicit understanding of this. But so the duality principle is duality between these two subgroups of G, gamma and U. We start with a gamma map from G mod U to X, and I will transfer it quite easily to a U map from G mod gamma to X. So I will take this guy here and build a U map to the same space. This is very easy. So look, we have this G here, and maybe I can map. Actually, I have this map from G to G mod U and to R2, right? And this is G goes to, if you think of it, this is the orbit map and U is a stabilizer of 1, 0, as we discussed. So this is phi of G of 1, 0. This is this map over here. Right? But now I will just a tiny bit torture it by using the fact that G is a group. So I can invert element here, and using the fact that this guy here is a G space. So I can multiply by G or act by G here. And let me add the G inverse action over here. So phi is not G equivalent.
if phi was G equivalent to begin with, this is a problem to actually discussed at the very start of the first lecture, then these two guys will cancel each other. But we don't know it. We do know it though for gamma. If G was an element of gamma, this thing here will do nothing. And actually, if you multiply G, maybe I should change this signs here just for convenience for myself. But if you multiply G on the right by gamma, this is the same as multiplying this G inverse by gamma inverse on the left. These two gammas will cancel each other by the equivariance of phi, the gamma equivariance of phi, right? This is to say, this is the universal property of the constant space G mod gamma. Whenever you have this map, what I just said is invariant for the gamma action on the right on G. Phi was gamma equivariant. Now this is a new map. Let's call this, I know. Let's not give it a name now. This is a new map. And this map is invariant for the gamma action on the right on G. So it factors through G mod gamma. Let me call this one phi, big phi. What about U? What if I now take this map? Maybe this is too dense. Sorry for not being tidy enough. Now, what if I multiply by an element of U on the left here? What will be the effect of that? It's like multiplying by U here, but also by multiplying by U inverse on the right here. But 1, 0 is U invariant, so it gets absorbed in it. So it just multiplying by U here is just the same as multiplying by U here. So this map phi is actually U equivariant, right? So we took phi in here, we put it into the machine, and got ourselves phi in here. Okay, does that make sense? But this is very nice, because on this space here, we have a U invariant probability measure. And if I map this space into R2, I can just push this probability measure into a U invariant probability measure on R2, right? So take this picture, this is R2 as you think of it, and there is a probability, there is a U invariant probability, actually ergodic measure, right? So somewhere here you see an ergodic measure. I don't know how it looks like, but maybe let's project this on the y-axis. Okay? I'm illustrating, maybe I will not write everything I'm saying, so you just have to listen. This map here that I'm encoding is the projection on the second value, on the y-axis. This point, or actually this line, goes to that point. This line goes to that point. All these points go to that point. This map is U invariant. Every orbit is contracted into one point. The map, the measure from G mod gamma, which I pushed to R2, and now I'm pushing to that axis, should be now a
probability measure on the line, yes?
Probability measure on the line, but U invariant probability measure on the line. And ergodic. For the trivial U line, U doesn't act anymore, or it acts trivially on the U line. What are the ergodic measures for the trivial action? Or what is a U invariant function to the rings? Maybe it's in here. An invariant function, well, this is not the infinity.
Never mind. I don't really think this. So the image mu is the measure here. Mu is the gene parameter here. Is the gene value probability measure. Is a delta measure. Right? So which point do we hit here? Could it be that point? This means that this orbit, this U orbit, this copy of R has a U invariant probability measure. Now, we all have studied, might have taught this observation of Lebesgue. Does not have an invariant probability measure. Shift now. Invariant probability measure. The only invariant measure on it is the Lebesgue measure, which is not a probability measure. I can scale it maybe, but I cannot make it probability. If you want a quick proof of this, use Poincaré occurrence. So I cannot, when I push mu to R2, I cannot hit that orbit. I do it only one orbit, or only one horizontal line. But it won't be any line but that line, right? So I'm hitting that line. And now think of this line and project it down to the x-axis. Again, by the same argument of ergodicity, I must hit only one point.
Excuse me, you are saying that this delta measure is delta at 0? This delta measure...
No, it is delta measure on the x-axis a priori.
I mean, at any...
On the y-axis, sorry.
Any point or must be at 0?
So let me put it, let me say it again. By ergodicity, and actually I'm using implicitly the fact that the orbits are nice, the dynamics is tame, the ergodic measure must be supported on a unique orbit. Now it cannot be supported on a big orbit,
Okay,
so it must be supported on one of these fixed points over here.
Why it cannot be supported on a big orbit?
Because if you are supported, it is U invariant,
Okay.
and the U action on an orbit is just the real action by shift on itself.
Okay.
So we get that the image of G mod gamma is a fixed point, a U fixed point, alpha 0 in R2 for some alpha. And now let's just so the image, maybe the phi big phi was the U invariant map. So this big phi is essentially a constant map. So now take x in R2. Maybe forget 0. I'm thinking of only up to null set, so it doesn't matter. Of course, I can present x
X is the image, and I will choose to take the inverse here of 1, 0. And I'm now just collecting, and I need to convince you that this alpha here is that alpha, which appears there implicitly, scalar multiplication by alpha. Then what? Then phi of x. Phi is the amount that little phi, sorry for choosing the same letter. Phi is the amount that I was interested in the first place. Phi of x, of course, is phi of G inverse of 1, 0. But this is by the definition of big phi is G inverse of phi of 1, 0. That is G inverse of alpha 0. And again, as before, this is alpha of G inverse of 1, 0.
But G is from G or from gamma?
Now G is from G. Now G is in G. I'm using the fact that big phi is constant. Alpha x. So and I'm done like this.
So I'm sorry for
Sorry?
but since you are dealing with maps up to measure 0, there is a little thing to check that if you change time.
There are little things to check, which I'm not doing everything so carefully now. I agree. Those things could be checked. Let me say that I'm leaving this on the later step. So again, the purpose of this 1 and a bit hours that I took now was to illustrate some ideas. It's not the importance of these specific questions that I want to explain. I want to explain various methods which will appear in this course again and again, and I will discuss in full. So what I want to do is to explain how nice ideas, and in particular, how the interplay between the tape dynamics coming from algebraic geometry and the Y dynamics coming from ergodic theory, which cannot agree somehow, give us non-trivial conclusions, the tension between these two topics. So I want now to single out things that appeared here, which I want to review in the next hours. So one topic, very important, is general theme of lattices in locally compact groups, especially Lie groups, as gamma is in G in our illustration. Another thing that we used and was very essential in our proof of ergodicity was the theme of metrics on coset spaces. We've seen that there are no invariant, G-invariant metrics on G mod U. This is again a general phenomenon that I want to explore. Very, very useful. Related topic. How more terms about vanish statistics. So I don't know, maybe you've all seen this. Maybe after my class we can discuss what is relevant and what is not. Well, I want to give some introduction to ergodic theory. start by introduction to measure theory and the foundations of ergodic theory, which I think usually are not discussed to the right extent in textbooks, etc. And I want to do it here, as time permits. Now, when I planned this course, what I started on discussing or preparing was algebraic, the dynamics of algebraic groups and algebraic varieties. I realized that if I will start with this, I will spend the course on that. So actually, maybe this is the most interesting part of what I'm going to talk about, but this is quite standard in a sense. And I think I will get to this point only when I have discussed all other things, because again, this is a swamp I can drown in. But unless, again, I want to have some feedback from you guys, and I can emphasize on this. Again, this topic, and of course that topic, and attention between these two. And next. Now the next topic is the connection again between the two previous ones, and this is measures on algebraic varieties. In particular, invariant measures with respect to group actions, and maybe the dynamics of the group action, algebraic group acting not on the variety itself, but on the space of measures. So here's a typical theorem. Maybe you are familiar with the Borel density theorem and its variance, which I do want to discuss. And eventually, taking this point of view, but in a more algebraic sense, I will discuss such things. Maps between ergodic spaces into algebraic varieties. This is algebraic representations so maybe I should start with what we are interested in this course is matrix groups, or maybe algebraic representation of groups. Take a group, try to represent it as a matrix group. This is of course an algebraic or linear representation of a group. The first invariant one studies is the Zariski closure of the image. This is an algebraic group, so it's much easier to handle than this abstract matrix group. We understand it much better, and we understand its actions on some algebraic varieties. The original group that we have might act in a different world. It might have some ergodic actions, etc. And what appears to be very successful is not studying only the algebraic representations of the groups themselves, but only the actions. So take this action group point and represent it. So here, you act on that, and you act on this, and represent this group point into that. Representation of ergodic actions. Out of this discussion, I will move Margulis superrigidity theorem, which I'll explain. So this is something I really want to do, and then now having done all that, maybe we will have some more time. I don't know. And then optional topics. Of course, I can get your input. I want to discuss probability. amenability. Using property T and finite generation of lattices, Margulis arithmeticity theorem, arithmeticity. Well, I should say, I want to discuss algebraic geometry not over only algebraic closed field, which is the easiest thing to do, maybe over the reals, as we did here, maybe over other local fields, over the p-adics, etc. So I want to discuss valid fields. I won't, probably I will not get to it. And using this, we can do some more. We can easily, we will prove things alternative, etc., etc., etc. Maybe I should stop here. There are various topics that are that fits naturally here, but probably I will not have much more space to these. Okay, so here's what I want to do for the remaining time of today. So until when do we speak? 12.
No mercy.
What I want to prove now, maybe very quickly, is the fact that I was proving that theorem without proving itself. The fact that SL2Z is a lattice in SL2R. Okay, maybe I will not get to it, but let me start. So there was this fact. SL2Z is a lattice in SL2R. Let's try to prove it. So let me recall. A lattice means this is a discrete subgroup, this is clear, but also that the cost space has an invariant probability measure on it. So clear. I hope this is clear, but maybe we'll discuss this in the future. So G mod gamma, notations are clear, has an invariant measure. On it. What I want to argue is that show that it is finite. 1 up to normalization. So there is an invariant measure and it is unique up to a scale. Finiteness means that I can think of it as a probability measure. So maybe to start with, I need to understand the space X, G mod gamma. What is this space? Concretely, not as a causal space. So what I will start discussing now is lattices in R2. Take R2, think of it as a group. Here is a lattice. Right? Here is another one. This is called never mind. So example Z2 inner standard. Maybe another. Take G in GL2R. And apply it pointwise to Z2. Here is 0. Here is 1, 0, and 0, 1. Here is 0. Here is 1, 0, and the image of 0, 1 under some matrix. You can explicitly write it down. So here, by picking these two, somehow I pick the matrix. The coordinate of these two, this basis, gives me a matrix G, and this presents this lattice G Z2 as GZ square in R2. Okay, so here is here's an exercise with a catchy name. This is the same exercise most of proved. So for some in a slightly different scenario, different setting, if lambda in R2 is a lattice, so every lattice is of that form. Or if you have lambda 1 in R2 and lambda 2 in R2, two lattices, I can find something like this. So this diagonal, if you replace R2 by, oh, okay. So this is easy to do, but now let me discuss so the space of lattices of all lattices, this is not yet the space I'm interested in, is isomorphic to GL2R. I just said modulus something. GL2R act transitively on that space. This is the content of that exercise. I can take this base point, Z square, and by applying G, I can take it to anywhere in the space of lattices of R2. So this space could be identified with a coset space of GL2R. And the stabilizer, or the group that should appear there, is a stabilizer of Z square itself. What is it? Thank you. Which we've discussed. This is almost SL2Z up to index 2. This is not almost SL2R. The index here is R star. The quotient of the indices is the positive real. Right? So there should be some invariant here. And this invariant is the core volume of the lattice. This is the determinant of that G that appears there is the core volume of the lattice. Is maybe here is the fundamental domain of that lattice. Here is the fundamental domain of that lattice. Here, by chance, they have the same volume. They are both unimodular lattices. I could have taken my G to be multiplication by 2. If I would have done that, I would have only points with parity, even parity, and that would be a fundamental domain. The volume here would be 4, right? The core volume. This is the determinant of that matrix. So go formal. Star is the homomorphism. You have absolute value to R star plus. This is the homomorphism as well. You have the orbit map. To the space of lattices. And of course, this map is invariant on this. So we get this diagram, and this is core volume. So the space I'm interested at is the space of lattices of core volume 1. So set, let me call it X now, to be a set of a space of unimodular, I think this is in that context self-explanatory, modular lattices. Now X is not all of it, but it is SL2 invariant subset. Actually, it is an SL2 invariant orbit, and I will leave you to check the following identification. Which we denote G mod gamma. So when we think of G mod gamma, we better think of, or we might think of the space of unimodular lattices and maybe I'll use this 5 minutes to do something. Okay, so I will use this point of view when discussing, when proving that SL2Z is a lattice. I will not prove it now, I don't have the time, so maybe I'll just put on the board some useful definitions. A primitive basis of a lattice, of maybe of a unimodular lattice, is xy elements of lambda such that the determinant of the matrix that I will read writing xy as column vectors these two are unit. This is the primitive basis. This is the primitive basis. Also this one and this one is the primitive basis. This one and that one is not. Right? The volume here is to be the volume, I guess, of that.
Could be minus 1. Could be minus 1.
No, so I want to read the orientation as well. This is my.
Almost 3 bases.
Sorry?
Almost 3.
This is, yes. It's just a name. A primitive vector I can give you two definitions. An element of a primitive vector, of a primitive basis. So here's an exercise to end this class with. X is primitive. So now lambda is given. Lambda is a fixed unimodular lattice. X in it is primitive if and only if X is not a non-trivial multiplication, integer multiplication of another guy, y in lambda. This is primitive. This is not. Okay? Sorry, what am I saying? This is primitive as well. This one is primitive because it appears here, for example. So this one is not. Okay? So solve this exercise, it's easy. How it really hit. Show it for the special case, lambda is equal. Show it for the special case, lambda is equal, and use the fact that all lambda is.
By multiplication will multiple, right?
Yes, integer. Yeah, I'm sorry for English. And I'm hurrying up now. So maybe just one remark about it. A, B. The GCD of A and B is 1 if and only if I can find C and D such that CA plus DB is 1, right? And this CD could appear here and complete it. I mean, this is but too much of a hint, everything. Okay, this is all for today. Thank you. Already. Questions? If you have questions, ask me.